But relating to the final exam, there was this interesting news snippet in the papers lately. Apparently, the Brookings Institute is reporting that countries such as the United States that embrace self-esteem in the high schools, joy and real-world relevance in learning mathematics, are lagging behind other countries in mathematics scores. So in places like the United States, where students are taught the importance of self-esteem and given lots of positive feedback in high school, the scores are substantially lower than in countries like, say, Japan, where they've perfected low self-esteem children, and they get much higher math scores as a result. And so I've been trying to think about how to use this information to improve your final exam performance. And, well, I've decided just to break it to you that you all suck. Not as students, of course, just as human beings. So I know that this might be a little bit hard for you to process right now, all at once, but think about how great you'll feel after you ace the final exam. You will come out of the final exam going, yes, I suck. So, needless to say, I did what any good student would do in this position. I got on Google and I started searching around for better information on how to suck as a student. And I found a truly awesome source of information that I want to bring to your attention. This is a unique and wonderful blog which is run by a number of very anonymous professors who take submissions from anybody. About 80% of their posts are things submitted by professors from across the country, and the other 20% is occasionally they give students a chance to talk back as well. And so this blog is really your lifeline for finding out what your fellow students at lesser sister institutions are doing, like in the state systems. And so there are these wonderful stories. I thought I'd share a few of them with you. Like, this is how to behave in order to suck as a student. One example is a professor talking about a student where she says, she once came to my office before a class, started to tell me that she couldn't come to class because she was buzzed and thought it would be disrespectful to me to attend the class. Then she wondered if I'd send her a podcast of my lecture or if she could just come by some other day and have me tell her what she missed during the class. Because in her words, like, wow, I just really need to go back to the dorm and chill out. Let this buzz wear off. And then she dropped by another time to say, when can I do a retake of the test since your instructions weren't clear enough? Here's another one. Another professor talks about getting a frantic email this evening from a student in their mid-level undergraduate course, and says that the student, she just now realized 9 weeks into the term that she took and completed this same course last year. It's exactly the same course with the same title and course number, the same textbook and the same assignments. She wrote that she didn't know that she had taken the course before. There's also the student who told me that he missed class because he was sitting in an empty classroom for an entire week. He told me he thought it was odd that there were no other students present, and finally went to the department office and found out we had moved across the hall. And another professor writes, a student turned in a late group report that he was responsible for typing, telling me that he had it done in time, but that he'd stuck it in the arm of his tiger costume. You see, he's the college mascot, and forgot it there and was unable to retrieve it for 2 days because it was locked in the sports department offices. Some students, fortunately, are very good at producing paperwork for when they miss exams or stuff. And this is something I would like you to emulate, like this student who, on the verge of being dropped for lack of attendance, brought his professor 6 of his speeding tickets to show him that they had all occurred in the late afternoon nearby, right before class. I was on my way, he shrieked, shaking the tickets. And finally, Oh, one professor writes about a student who asked for a week's delay in taking a major test because her cousin had died. When she arrived for the makeup exam, she gave me an obituary notice clipped from the paper. Not that I'd asked for it, says this professor. As she started taking the test, the professor noticed that the date of the paper was on the flip side, and it showed June 11th, 2004. This was a very recent occurrence. Like, this happened in 2006. Professor stopped her and noted the date, and for a moment she looked startled and then said, "I know, I just found out." So, I gotta tell you, every time I read this blog, it makes me really grateful to be teaching at Berkeley where students don't have pizza delivered in the middle of the lecture. And so, I guess you don't suck so much after all, but don't let it go to your head, okay? Today's lecture is on garbage collection. So this is about what Java does to save you a whole lot of pain and agony that you will learn about when you start programming in C or C++. Java cleans up your garbage for you. A lot of other languages don't do that. And it makes a huge difference, actually, in coder productivity to have a language that does garbage collection for you. What is garbage collection? Well, objects take up space in memory. You can allocate a bunch of objects and then forget about them and then never use them again. Do they still take up space in memory, or can you reuse that space for new things? Well, in languages like C or C++, you have to explicitly say, okay, I'm done with this piece of space. You can reuse it for a new object. But Java just kind of figures it out for you. And the way that Java figures it out for you uses algorithms that we've learned in class. So the Java virtual machine that executes the bytecode that you compile your programs into has hidden data structures that you cannot see. You cannot directly access them through your Java program, but they're there to help Java figure out which objects you're still using and which objects are garbage that it can recycle and reuse the memory from. So again, the Java virtual machine also known as the JVM, which is the thing that runs your program. Basically uses lots of hidden data structures to manage memory. And although those data structures may be hidden from you so that you can't access them through your Java program, they are data structures that you understand, things that you know about. And so it's good to have a good mental model in your head of when Java can reclaim your used objects and when it can't, because that'll help you sometimes to program your programs in a way that makes it easier for Java to do garbage collection and keep your program efficient. So now, you don't have to know anything about garbage collection to be an efficient Java programmer, but it could help in this one area. If you have programs that are creating a huge number of objects and you're having trouble running out of memory, sometimes it's good to know how to let objects go. So here's a peek at what's going on under the hood. In Java, garbage collection starts at the roots. Now, the main directive of Java's garbage collection is to never sweep up an object that your program might use again. And any any object that your program might use again is called live. So again, the main directive is do not sweep up live objects. And the opposite of live is garbage. In other words, garbage is an object that your program simply cannot reference again after a certain point in time, basically because you've lost all the references to it. So Java's design makes it possible for the JVM to decide whether or not you can ever reach an object again. And it begins, like I said, at the roots. A root is any reference variable you can access directly. By directly, I mean without going through another reference. So what kinds of things are roots? There's a few simple kinds. Or at least, here's all the kinds we know about. They're local variables. Any local variable in any stack frame on the stack might reference an object, and those objects are alive. The other one is, of course, you can have class variables. And class variables are always available. Remember, class variables are the ones that we declare static. And as long as those class variables are references, they're roots too. And those are the two kinds of roots. Now, an object is live if it is referenced by a root, or if it is referenced by another live object. Now, you'll notice that this definition is recursive. I'm a live object if some other live object references me. So another way of phrasing this is that an object is live if it's reachable from the roots. And so here's another way to think about it. Think of every root and every object as a node in a graph. If a root or an object references another object, think of that as a directed edge. Now we have a directed graph. And when I say reachable, I'm talking about graph reachability. In other words, there is a path from a root to the object in question in that graph. And if so, then the object's live and could be referenced again because you might follow the chain of pointers to get to it. So, any questions about this so far? Yeah. So when garbage collection runs, it does do depth first search on this graph. As for the data structure, there's sort of an implicit data structure, which there are hidden data structures that tell Java things like which memory locations on the stack are reference variables, so it knows where the roots are. And there are hidden data structures that link all the objects that your program ever allocates together in an invisible linked list. And so with these data structures, Java can solve this reachability problem on the graph. Other questions? Or did that answer your question? Okay, good. So as I just said, the way we solve this reachability problem, well, the way Java solves it, is you run depth first search from the roots. Now, to do depth first search, every object that you can visit needs a visited tag. So, and that's one of the things that Java hides from you. So this visited tag takes a bit or two of the object's memory, but it's hidden. And there are actually pretty tricky ways to program these visited tags that I'm not going to talk about today. Now, before I can go on and talk about the details of these hidden data structures, you really have to understand a little bit about a computer's memory. So I'm going to give you a very brief preview of some of the stuff that's in 61C, like the whole notion of memory addresses, because we need to know this to know what's going on under the hood in the Java virtual machine running on our hardware. So one of the things that Java tries to hide from you, but languages like C will expose to you, is the fact that in your computer, memory is one big array. It's just one huge array, multi-megabyte array of bytes. And those bytes have indexes, which are called addresses. And so your memory basically looks like this. Only, of course, if you have a couple megabytes or a couple gigabytes of main memory, this goes off quite a ways to the right, obviously. Now, modern computers prefer to read and write memory 4 bytes at a time. If you have a 32-bit processor, that's what it means, is that it's optimized to do 4 bytes at a time. Usually runs fastest if it's doing it at a memory address that's divisible by 4. So we can treat memory as if the addresses are only every 4th address for the most part. Now, when you declare a local variable, you are naming a memory location. Now, you get to pick the name. When you say int x, you're naming a memory location x, but of course, Java gets to pick the memory address where x is actually stored. And one of the whole purposes of compilers and computer languages is to hide this bookkeeping for you, so you don't have to think about what address x is stored at or keep track of it when you write your code. So maybe I have an array that looks like this. And we're just going to look at addresses divisible by 4, because that's what works fast. And this array goes both directions. So if I write int Bob in Java, Java goes ahead and finds me a free memory location that's not being used for anything else and names it Bob. And when you write in Java, Bob equals 3, the Java virtual machine duly goes, oh, the programmer wants me to put 3 in the box named Bob. So that's how that works. One of the interesting things you can do with memory is you can actually store memory addresses in memory. And when we use memory addresses as data, like we actually have a memory address stored in a memory, then that's called a pointer. So for instance, in C, I can declare a pointer, call it PTR, right there. And I can store in it a memory address like 216. And when I store that memory address, the way that that is supposed to be interpreted is this is a pointer to Bob. Well, it's a pointer to whatever is in address 216, which just happens to be Bob. Now, Java uses pointers a lot internally, but it treats them like confidential information. Java does not want to give you guys the ability to accidentally shoot yourself in the foot by assigning a random number into this box. And so Java only allows you to use memory addresses in a very limited way. References are like pointers, but they're not the same thing. And you're not allowed to store arbitrary numbers into a reference value. You have to store only a pointer that points to the right kind of object. And Java imposes a strong discipline on you to do that, which actually saves you from a lot of errors that you would probably have otherwise. Debugging code is much harder if you don't have a compiler looking after your back like that. And the data structures that Java uses to store objects use these pointers as well. So Java will lay out memory for objects for you, and then it will have pointers between the objects that knit all of the objects together in a big doubly linked list. That way, if Java wants to do one pass over every object in memory, it can do it by following the pointers in that invisible doubly linked list that you can't access, but that the garbage collector uses all the time. So questions about that? So that gives us what we need to talk about a particular algorithm for garbage collection called mark and sweep. All right, a mark and sweep garbage collector runs in 2 phases, the mark phase and the sweep phase. So the mark phase does depth first search from every root. And as it does so, it marks all the live objects. And yeah, while the Java virtual machine is doing this, your program is frozen in mid whatever it was doing, probably creating an object, because the garbage collector usually gets triggered when you try to create an object and space is short. Now, once the mark phase has found all the live objects, anything that's not marked is garbage. So the sweep phase does a pass over all of the objects in memory. So remember that I told you that all of the objects are secretly connected in an invisible doubly linked list, or maybe some more complicated data structure. The sweep phase just traverses that entire list or tree or whatever data structure the Java virtual machine guys want to use today and gets rid of the garbage and deallocates it and marks that space as being free for reuse. And again, the thing that enables this to happen is that the JVM has simple but invisible data structures, often as simple as linked lists. That keep track of all the free and allocated memory. So similarly, the activation records that are on the stack are represented as a data structure that the JVM can read and go through and find all of the stuff that is roots. So it knows, based on that data structure, exactly which memory addresses on the stack represent references to objects. And so it can use that to start the mark phase. So, okay, that's all I wanted to say about that. Any questions? So there's one detail that comes up when you're doing this mark and sweep, and it's called compaction. And it's about this problem. So a typical program allocates and then forgets a large number of objects. One problem that happens is called fragmentation. Fragmentation is the tendency of free memory to get broken up. And in the worst case, the memory might get broken up into lots of small pieces that are far apart and maybe prevent you from having room for a large object. So maybe your memory, think of it as a big long array like this, and you've got an object here, and an object here, an object here, an object here, but all the objects between those have died long ago because they just weren't used for long. The problem now is that if I want to allocate an object that's about the length of this eraser, there's nowhere to put that object. Now, there's lots of free memory. More than half the memory is still free. There should be enough memory to allocate this eraser, but there's no specific spot where the eraser fits. So I want to do something about that. And so compaction means I take that bunch of objects and make them compact. And so what will happen is, during the sweep phase, we will actually take the objects from left to right, and we will move them all the way to the left. And look at that. Now that frees up a lot of memory I can reuse now for larger objects that wouldn't have fit before. Say here. So if a garbage collector does that, we call it a compacting garbage collector. And a compacting garbage collector moves objects during the sweep phase. There is a special trick we need to make that possible, which I'll talk about next. But before I do, any questions about the basics? Yeah. This is linear in the amount of memory that you're compacting, like the total size of the objects that you're compacting. So the sweep phase basically has to go through over every object once and copy all of its bytes. The mark phase uses depth first search, so it's linear time in the size of the graph. And yeah, that's it. Other questions? All right, so here's the trick that we need to make compaction possible. And here's also a question. I've been talking about references all semester long, but I never actually told you what they are, really, at the machine level. That's something that's been sort of abstracted away for you. But here's how they're typically implemented in JVMs, and certainly in the Sun JVM. Here's the problem, first of all. Suppose that I have an object here, and there are a bunch of references to it from other objects, from local variables, from the roots, whatever. So I've got a million things pointing to this object. How can I just go and pick this object up and stick it over here? Don't I have to go back and find the million things that point at that object and give them the forwarding address to the new location of the object? And the answer is no, and that's because this is how references work. In the Sun JVM, a reference is not a pointer. It is something else called a handle. Okay, that doesn't help very much. What's a handle? A handle is a pointer to a pointer. So here's the idea. The before picture looks like this. There's some object here. There's a bunch of references that point to that object. And there is a special table of pointers to objects. And somewhere in that table, there is a single pointer to our object. And all of the references don't point to the object. The references are actually pointers to that pointer. And so if I want to pick up the object and move it over here, well, that just means that I need to change this one pointer in the box so that now it points to the object in its new location. And all of the references still point to that pointer. You never move one of these references or change one of these references because there could be a frickin' million of them. What you got to do is you change the one at the bottom and the others never change. So that means we can move an object. This particular pointer is never allowed to move. But not being able to move a pointer is not nearly as big a deal as not being able to move an object for two reasons. One, pointers are much smaller than objects. And two, since pointers are all of the same size, we can have a special table for the pointers, and you never have to worry about fragmentation because if every pointer is 4 bytes long, then you're never going to have a big pointer that won't fit in a little gap. That doesn't happen. If all the pointers are exactly the same length, then storing things in a table where things are disappearing and reappearing quickly is much easier. And so again, these second pointers are kept in a separate table. And that table is small enough that we don't have to worry about compaction problems in it, and it's all pointers, so we don't have to worry about compaction problems in it. So are there questions about that? Okay. That's mark and sweep garbage collection. That's one way to do it. Here I'm going to show you a different way. Well, it's not completely different. It's similar. It's a relative of mark and sweep. Here's the thing. It's faster than mark and sweep because it only does one phase. Or to be more specific, it only visits each object once. So whereas mark and sweep visits each object twice. So in general, it runs almost twice as fast. The memory is divided into two separate spaces. And those are called the old space and the new space. Basically, the old space is where your objects are now. The new space is where you're moving them to in just a sec. So the copying garbage collector does this. Starts the same. It finds the live objects by DFS as usual. But when it encounters a live object in the old space, it immediately moves it to the new space. And when it moves the object from the old space to the new space, it does compacting as it goes. So the object goes into the new space in the first available memory location. So compaction is part of the deal. And one of the nice things about this is once you've moved all of the live objects to the new space, you just forget about the garbage objects. You don't have to explicitly walk through the garbage objects and deallocate them. You just blank out the whole old space. And when I say blank out, I don't even mean you walk through it and write 0 bytes into it. I mean you just forget that there's a data structure in there at all. And next time you need to use it, you reconstruct a brand new data structure from scratch. So you just forget about whatever's in memory in the old space. And you can do that without any computation at all. And then the next time you need to do a sweep of garbage collection, the new space and the old space trade places. So it's really like you've got a space A and a space B, and half the time you're copying objects from space A to space B, and the other half the time you're copying objects from space B to space A. Yes? Absolutely. So this is the big flaw with copying garbage collection in its basic form, is that it wastes half your memory. But there is an advantage. It's fast. It's faster than mark and sweep. The disadvantage is one that at first sounds totally unacceptable, which is that your memory is cut in half. And indeed, it would be completely unacceptable if that's the only component of your garbage collection system. But actually, we can build a better garbage collection system by combining several of these ideas. Question? Is it worth it if you what? If you to get more memory for yourself? You mean more than what's on your computer? Or? So compaction definitely helps free up memory for you, for sure. So yeah, you're doing better than you would if you didn't have compaction at all. Maybe even better than if you had all of the memory instead of just half of it and didn't use compaction. So that's true. Well, however much you allocate. So your Java program might try to allocate all the memory in the entire computer, and then you get half of it. That would be an antisocial thing for your Java program to do against other processes running at the same time, but in the dumbest version of this, that's how it works. The smarter version is that you start small and then you keep resizing bigger as you go, and that's what is done in practice. But it still has the problem that you can only use half the memory you've allocated, and so if your machine has 2 gigabytes total, that only gives you access to 1 gigabyte, which is not good. But where this is good is when it's just part of your garbage collection system. So what time is it? I have 8 minutes. I think that's enough to talk about. Oh. Well, I would talk about the next memory collection system, but that's in tomorrow's notes, and I didn't bring them, so go home. See you Friday. Enter the tournament.